All right, so why don't we begin? All right, sixth lecture, the section of 364. And today we will be talking about gradient descent, pretty much tying everything we've learned over the past 2 or 3 lectures together. Just how we calculate, well, I mean, we've gone through how to calculate the gradients using computation graphs extensively. So now we're going to actually use the gradients to try to find the minima of functions, to try to, and more importantly, to try to fit the functions to a particular data set, a rudimentary data set. And so with all of that, doing all of that, that'll get us nice and ready for more advanced data sets, more advanced functions, all of that good stuff that you typically see with deep learning. Okay, so today we're just going to focus on some simple functions. Simple functions, finding a minimum of those simple functions, and then the next couple of weeks we're going to gradually increase the complexity of our networks. Okay, until we're at the most advanced deep learning, deep nets. Okay, so let's start off with motivation behind gradient descent. So most of machine learning focuses on finding the minima of a particular function. This is what's, you'll often hear the word minimizing the loss. Loss itself is a function. So most of machine learning is focused on minimizing that function. Okay, so with the reason, so we'll go over that in more detail why that's important later. But for right now, we just want to try to find the input values for which a function f is minimized. Okay, that's what we're going to do for the next couple slides. We have a function and we want to minimize it. We want to find the inputs that give you the smallest value possible in that function. So for some functions, this is very easy. For some functions, you could very easily derive the actual minima by simply looking at the functions and solving for them analytically. So for instance, with sine x, the minima occurs at 3/2 pi, because it's a sine wave. You got a sine wave, and then the minimum of sine x is at when f is equal to -1. So f is equal to -1 and 3/2 pi. I hope I'm doing that right. Yeah. You have other functions. For instance, you have a basic polynomial function, to the basic power 2 polynomial function, where you know x is minimized at a particular root if a is positive. If a is not positive, then it's otherwise minimized. If a is like negative, then you got the parabola that goes in the negative, that's not a cup, it's a, what's the word? It's a hump? That's not the correct word, so let's go with that. It's a hump, and therefore the minimum value occurs at, sorry, okay, there we go. Oh. The minimum values occurs at either end. Oh. Is this okay? Lecture, come on, there we go. Okay, oh, strange. Okay, I got a feeling I jiggled the computer incorrectly, and then did something. Okay, anyway, so we can solve for this analytically, but then there are complex functions where we can't solve for things analytically, right? Trying to get the minimum of something like this is fairly difficult. Okay, we could solve for it. I have faith in you guys. I'm sure if I put that out as a homework question, you could expand out everything. You could get the roots. Can you get the roots? Yeah, you could definitely solve for the roots of a polynomial 6 equation, but it would be pretty difficult, right? It would be pretty difficult, pretty time consuming, and the most offensive thing is that it's going to be time consuming and you could never reuse that code again if you solve for a particular function. That's the computer scientist's worst nightmare. Doing something that you could only do, that's only useful once. There's a famous quote, I think it's attributed to Knuth, it's attributed, or Linus, that basically a computer scientist will spend 3 hours doing a task that would take 1 hour just doing it manually. That's the thing right here. You don't want to actually make something. You don't actually want to solve a particular equation directly because that effort basically isn't able to be reused. You want to do something that's more general, right? So if we graph this, there we go. If we graph this, we see it's a basic parabola, and the minima is not at 0. It's not even at 1. It's somewhere around here. 0.75, 0.8, something like that. But we need a more exact solution. So, a major thing. How do we find a more exact solution? What do you guys think? Without PyTorch. This is we're now in basic algorithm. Not basic algorithm. Oh yeah, let's go with basic algorithms. Now back in algorithms. How would we find it? How would we find a minimum? Oh please, yes. That's true. We could take the derivative of the function and set it to 0, but then that would require us to actually mess with the function a good bit and find the derivative of the function, which I would like to avoid if possible. Also, if we set it to 0, then we would have to still solve for that function, right? So then we would still have to use probably SymPy to solve for the derivative of the function equal to 0, find the value of x. And I can tell you from experience, as much as I have a deep affection for SymPy. The people that are working on it for free are amazing programmers, but I could tell you it's incredibly buggy. If I had a choice, I would never want to use SymPy because it is very buggy. And if the equations even get marginally complex, there are all sorts of regression issues. I could opine about that all day. But yeah, but that is an option, but it's not the ideal option. Let's go with that. Any other ideas? Yeah, let's go. Yeah. Could we do the min operator? Oh, that's an interesting thought. Yes, we can, because this is Python and you have all sorts of functions available to you, right? You can, but it's not going to be super fast. I could also tell you from experience. I love Python, but this is the awful thing about Python is that it gives you too much in your toolbox, and you end up using suboptimal functions. So I would like something a little faster. Yeah, please, Thomas. Yeah, I mean, yeah, that's probably the simplest approach where you basically it's not brute force. Brute force would sort of be a grid search, which would be even worse. But that's the iterative approach. So what Dominic is saying, we just guess a value of x. We could start off with x equals to 0, and then we could say, all right, if we change x a little bit, let's say we try x equals 0.5, does f get smaller? Yes. All right, that's our new x. If, for instance, if we start off at x equals 1.75, and we say now x is equal to 0.8, we say, oh no, the function is getting bigger, we'll go the other way, right? That's just a basic iterative approach. That's effectively the pathfinding approach in certain ways. Oh, you know what? I think you would classify that as a greedy algorithm also. The definition of greedy algorithms aren't well set, but I'm thinking about Donald Knuth's Art of Computer Programming, and I think that's how he classifies certain greedy algorithms. That basically you take a point, and then you say, all right, I'm going to look to the left, I'm going to look to the right of that point. Whichever way is smaller, I'm going to move down, right? So that's a nice iterative approach. Come on. Oops. So how do we do that? Well, we could implement a nice piece of code. Ooh. Oh. There we go. While true, we just simply set an initial value for x. We have an x and we set it to an initial value. What does x start? Well, in this case, we're guessing 1.7. We say, okay, we start off with an x at a particular value, and we look at the current value of x, and then we change it, we perturb x a little bit. We add a small little step, and then at every sort of loop iteration, f next, if the function over f of x, if the function increases, then we go the opposite way, pretty much, right? Because we're trying to find the minimum. So if the function increases, we say, okay, clearly the delta we took, the delta we're taking is positive in this case always. So if the function is increasing with the change in delta, then we made a mistake. We're going to go the reverse way. Okay? So, and then we go on, so on and so forth. And yeah. So if we do all of this, if we do this while, and we can't do this forever, of course. So if we have, for instance, a tolerance parameter, I forgot what the tolerance parameter. Oh yeah, 1 e to the negative 5 convergence criteria. If we've set a tolerance that we end if we get a delta that changes by a very small amount. If when we apply delta, it changes by a very small amount. Then we sort of find our way, and we get a graph like this. Oh, there we go. Sorry. We get a graph like this. Okay, we start off at a particular value. We keep going. We test the change in x. We see, oh, that change in x, it goes down. Did I explain that? F of x next equals dots. If the function value, reduce the step size and reverse the direction. Oh, I should have reduced the, I did both things. So we did reverse it, I should have explained that. So as we're going down, as we take each step, as long as we're decreasing, we take another step towards the minimum. And then as soon as the function increases again, we reverse the change. And then we also, at the same time, we're dividing this step size by 2 when we start increasing to sort of get to that minimum. Okay? So, nice little iterative algorithm there. Seems to work pretty well. Right? What's the issue? Are there any issues with this? Yeah, please, Alex. Yeah. That's true. So let's hold off on the true minimum talk for a moment. I'm going to address that because that's true of a lot of algorithms, unfortunately. But the major issue with this iterative algorithm is that yes, we are starting off relatively close to the minimum because I saw the graph and then I entered that graph in. Now, if for instance my delta start is something like, I don't know, 0.000025, and then I started x at, I don't know, 10 or something, right? Then I got a feeling I have to change the x limit. Yep, I do have to change it. Let's do that. Let's see what we get. Yeah, then we're going to end up making a whole bunch. Oh, I didn't change the y limit. Let me see. Y limits. I'll do 850. Even that's not enough. Okay, well, you guys get the point. We do a whole bunch of unnecessary steps where we didn't really need to, right? So not ideal. Also, it's a very serial process. That's the major, that's I think a bigger issue than even the initial parameters, right? Every algorithm, you have every iterative algorithm, which gradient descent is pretty much. You have this issue of correct start values, correct the learning rates, et cetera, right? So by that measure, this isn't too much worse. But it is an incredibly serial process because you have to basically get a point, you test the point, and then you go return back. And then it's hard to generalize, right? But this works pretty well, okay? It works pretty well. The major thing that really we could optimize is this part here, right? Instead of calculating the function at a new point and calculating a function and then estimating and then just taking a predetermined step. Really, let's look back at our parabola. If we're at this point, and we know, if we're at this point, and we see that the function is almost vertical. It's almost vertical. Why would we only take a step size of 0.0025, right? Like we're at this point and we're like, it's decreasing by so much, and we know the minimum occurs when the derivative is equal to 0, right? So why would we only take a step size, why would we only take a small little step size and move down our function slowly? But when we're at this point, well, we say that to ourselves because we're like, we don't know we're at this point. What if we were at this point that was relatively close to the minimum? In that case, we should take a very small step size in order to get to the minimum. Because if we didn't take a small step size, for instance, let's change some things back. We have our original function again. Let's take a huge step size. Let's take a huge delta. We're going to just put a 10 right there. What will happen? Something terrible happens, right? In that case, it's the whole thing becomes unstable because we're taking huge step sizes, we're doing a lot of extra effort, and we're going around the curve and jumping back and forth. That's not what we want either, right? So that step size whole thing is really the flaw of this idea. There is a good idea in here. The good idea is that we have a step. We start off at a certain point. We take a step towards the minimum, right? But the bad idea is that we're just setting our step size manually. So how do we resolve that? Yeah, we start a value, wrong increment. So the question is, how do we resolve that? And we resolve that by looking at the derivative, right? When we look at the derivative and we see the function is very large, for instance, over here. Can we go back? Yes. When we look at the function again here, when we're way away from the minimum, we could look at the derivative and we see, hey, the derivative here is super large. So because the derivative here is super large, there's a pretty good chance I could take a big step and I still won't overstep the minimum, but I'll get a lot closer to the minimum than I otherwise would have if I just take a small step constantly, right? But over here, the derivative is very small. And in fact, we know the minimum is when the derivative is at 0. So if the derivative is very small here, then we're probably somewhere close to minimum. So we should adjust our step size to be small because we don't want to overshoot the minimum, right? So our descent in this case, so we want our descent to be controlled by the gradients, and that is why we use a process called gradient descent. That's where the name comes from. It's simply the idea that we have an iterative algorithm, and the step size, instead of manually setting it and adjusting it every so often, instead of that, we simply make the step size controlled by the gradient. And as long as it's controlled by the gradient and our learning rate is correct, other parameters are correct, we should have a very stable path towards the minimum, right? So, idea behind gradient descent. So if we want to minimize our function, we have to step in the direction of the negative gradient. We already saw that with the iterative algorithm. We basically perturb the function a little bit. We take a step to the left, take a step to the right. We take the step that leads. We take the direction. Yeah, the left or right that leads to a smaller value. Same thing in here, except we don't really need to take a step to the left or to the right. We simply say if the gradient is positive. If the gradient is positive at that point, then what does it mean? It means the step to the right is going to be larger than taking a step to the left, right? If the gradient is negative, then it means the step to the left is going to be larger than going to the right, right? So all we need to do, as far as what direction we go along the curve, is simply take a step in the direction of the negative gradient. That'll help us minimize everything. And then the idea becomes, supposing we have a differential function f of x, and that we would like to minimize, but we cannot find a closed form solution for, or even if we could find a closed form solution for it, we're just not in the mood to do that. We are going to initialize a guess towards that somewhere in the vicinity of the minimum, hopefully, but maybe not. It's just a random guess works just fine. Then we'll update x by the next step by moving its value opposite to the gradient, i.e. x of k plus 1 is equal to x of k minus the gradient f of x, minus the alpha. And this alpha is what's called the learning rate. This alpha is the step size that we did in the iterative algorithm, but this alpha is also what people commonly refer to as the learning rate. And why is that important? It's because, as we saw earlier, you don't want to take huge steps, right? But you also don't want the steps to be too small. So optimizing the alpha is kind of important. The gradient only tells you the direction of the iteration of the steps that you should take, and how the step size should scale, right? It doesn't tell you what the actual value of the step size should be at any particular point. The gradient gives you a good idea of how a step size near the minima should be relative to a step size that's far away from the minima, but it gives you a relative measure, not an absolute measure. I don't think there is any. Well, in complex functions, there is no optimum step size, right? So in that case, the gradient gives you a relative approximation of how to scale the step size, and so this learning rate sort of gives you the absolute value, the absolute step size to start at, and sort of absolute value that scales as you come closer to the minimum or not. Does that make sense? So we modified our iterative algorithm again, and so the important thing here is to find the gradients. For the moment, we know that there are better ways to calculate the gradient other than symbolically, but since we're programming this as humans, we're taking this one step at a time. And so let's keep the symbolic computation going. We're gonna step away from symbolic computation later in lecture, but for now, we have the original function, which is a 6th-degree polynomial, and now we can take the derivative of that and get the gradients in this case, which would be a 5-degree polynomial. Does everything make sense? Derivative of 1/3 x minus 1 to the 6th is equal to 6 times 1/3 to x minus 1 to the 5. Yep, all that makes sense. Okay, so we have the function that we want to minimize, we have its gradients, and we have the process here. So from a starting point, x0 equals 0, we'll choose a learning rate, and we'll run this gradient descent for however many iterations. 100 iterations seems fine. These are all arbitrary values I'm picking out of the air. And then we'll plot the values of x and see what we get. So we have a piece of code like so, and I am gonna run here. We have a piece of code here, and that's exactly what we're doing. We have an initial guess for x. This flickering is driving me nuts. Oh my god. I could see it out of the corner of my eye. Like, I feel bad for you guys more than anything. But also, I feel bad for me because it's like, I can't stand that sort of thing. I swear, I've been asking them to fix it. I think it's a loose connector here. Come on, you can do this. There we go. Okay, thank God. All right. By the way, next time, just tell me. You guys don't have to stand for this. You're paying way too much tuition dollars to have to stare at a screen that's like flickering red constantly. All right. So we have an initial guess for x. Again, what did I choose? 1.7. Well, yeah. I'm doing this because I know sort of what's going to happen. I mean, where the rough minima is, but it's not necessary to be that close to the rough minima. Anyway, we choose a initial guess for x. We choose a learning rate. So 1e to the -3 is pretty common. People always choose it. Like it's very common. So a rule of thumb is that the more complex your model, the smaller the learning rate should be, and the less complex your model, the larger your learning rate should be. That's I don't know why that is. I genuinely still have trouble understanding. I think it's just that the number of parameters that you need to optimize. If there's more parameters, the learning rate should be smaller, so all the parameters get optimized well together versus reverse. But I don't think there's a theoretical foundation behind that. Yes, please. Yeah.
Do you like change your learning rate? They get bigger as they start, you get smaller, or you don't need to do that?
So you don't need to change your learning rate. Ideally, the gradient should be changing your step, right? So because the gradient is changing your step, that ideally you won't have to change your learning rate. There are papers that have argued that you should change your learning rate during fine-tuning. But that seems like a lot of work. But there are papers that do that. And actually, the more advanced optimizers, I think Adam does that. I have to check the exact algorithm that goes into Adam. But yeah, ideally for this step, we're not going to change our learning rate. But we get the initial value. We have a gradient that we calculate manually here. And then we simply say the next value of x is simply x minus learning rate times that gradient. Okay? And this is just to append the values of the gradients. This is just for the graphs that we want to do later. And then we just do this for some number of iterations, okay? So before we had a while loop that we took a while loop and we did it until the step sizes got small. Remember, before the iterative algorithm, we had an initial step size, then we halved it if the step size kept going, if the step size increased every so often, and then once the step size became small, then we were like, okay, we're close enough to the minimum. This, we don't even need to do that, right? We don't even need to have that logic. all we're going to do is just run it for a bunch of iterations. Ideally, the gradient should make the step size small itself as you get closer to the end, and we don't need to bail early, but we can always, if you wanted to, you could always put a condition here that says, like, if the gradient is below a certain value, just break the loop, right? But we're not doing that in this case. We're keeping it very simple, okay? So we plot it all out, and what do we get? We get the same function as before. It's a little stretched out because I wanted to make the layout of the 3 different graphs look nice. But what we see is that when we start out at 1.7, we're taking some big steps towards the minima. So over here, the step size is pretty huge. And in fact, yep, right here, magnitude of the gradients. So in fact, we see that the magnitude of the gradient is pretty large. We multiply that by the learning rate to get some step size there. So we start off with a huge step size. And then as we move closer to the minima, from here, we see step size becomes a little smaller. Why? Because the gradient becomes a little smaller. Same thing here, next iteration. Step size becomes a little smaller because the gradient becomes a little smaller. And so we do that 100 times, slowly getting towards a minima. And in fact, if you see the value from x, you can see a exponential decay starting from 1.7 and ending right around 0.8. I think it's a little larger than 0.8. It's like 0.805 or something, or 0.03. But yeah, that's the idea behind gradient descent. Very, very simple. It's simplified a lot of different things. All we do, all we need is to calculate the gradient, multiply it by learning rate, and then take a step. Okay? And if we do that, notice there's no trouble of overshooting, right? Is there a problem of overshooting in this case? In this case, there isn't. Can we overshoot the minima, though? Please, yeah, Patrick.
I think yes, and there will be a case where there's a very tiny cup, and on either side of it, or on one side of it, it's going up, on the other side it goes down. And if you start on the side that's going up, and your step size is too large, you could overshoot that cup, in which case you would end up on the other side.
I do agree. Definitely agree with you that if you start off with, if you have something that's very very small, like I totally agree with you. If the graph itself has like a very precise minima, absurdly small minima, and we kept all the other parameters the same here, then yeah, we could overshoot the minima, right? Because it's, even if the gradient is like negative, the gradient is like some value, like negative 100, then we'll overshoot it. We'll go past the minima onto the other side, and then the gradient there will be positive 100. We overshoot it, and we bounce back a couple times. I agree with you. Is there a way we can modify this just to make it overshoot here? Yeah, change the learning rate, right? What should we make the learning rate? And actually, I'm going to make the initial guess closer to x, but I don't know. Let's make it something like there. What happened? Oh, the result is too large. Oh, boo. You failed me, Python. Don't give me that. Oh, that's pretty funny. I'm going to make it, why was 100 too large? I did this. Oh, at 34. Oh, I see. All right.
You can decrease the number of iterations.
Oh, yeah, I could decrease the number of iterations. Yeah, why am I doing this? Yeah. Good call. Why are you doing this? Okay. Yeah, pretty much. So you pretty much see what happens there. And actually, I'll decrease the number of iterations even further. How many was this? 10? So all I need to do is go to 9. Then it'll illustrate the point much better. There we go. Okay? So if the learning rate is too high, what's happening? We basically start off very close to the minima, but our learning rate is too high, so the amount we change our step size overshoots it, and in fact, it goes past, and we end up at a larger value, a larger absolute value than we were before. But the model is like, no, don't worry, we could do this. And so we overshoot it again, and we overshoot it again, and we overshoot it again, and unfortunately, it gets out of hand very quickly, right? Yeah, fun little exercise, I think. But yeah, so you could make this unstable if you make the learning rate too large. But we don't necessarily need to worry about that. Will this keep increasing forever? I know Python has a problem with the magnitudes being too great. But do you think this will keep increasing forever? Actually, this will make a good... Oh man, I wish I thought of this for the homework. This would be such a good problem. When we discuss learning rates, let me just write a note to myself. I want to come up with a good animation for this one. We'll leave it for next time. Okay, anyway. Okay, so let's leave that. Okay, so that was fun. Okay, so that makes sense to everyone, right? So let's move to the next bit. Do we try? There we go. Okay, yeah, so gradient descent has a lot of there's entire textbooks written on gradient descent. I'm pretty sure there's at any major machine learning conference there's an entire section devoted to optimization algorithms. So yeah, the world of optimization is very, very, very large. So I'm sure if you have an idea, if you think of an optimization that you could do, well, it's not guaranteed that it's been thought of before, but so you feel free to throw it out there. But there have been a lot of ideas on how to better optimize large models, and you guys will experience a lot of the major ones throughout this course. But yeah, there's a course in ECE called ECE 490, Introduction to Optimization. If you want to take that. Or if after this course, that should help you. Okay, so there is a drawback. There's a major drawback of gradient descent, which Dominic pointed out so eloquently earlier. I mean, it's not just a drawback of gradient descent, it's a drawback of any iterative algorithm where we're trying to find a minimum. And that's simply that it finds a minima and sticks there, right? So for the previous function, that was fine. You know, we had a function that had one minima. And so whatever we initialized x to, we were guaranteed to get to that minima. Okay? So that's fine. That's ideal. But that's not usually the case when you're dealing with large models. You have a bunch of different parameters. You have very complex you have a very complex parameter spaces, and you could have multiple minimas. And so to illustrate this point, let's go and look at a function that we've been staring at for a long time these past couple lectures, namely f of x is equal to sine x, is sine of the log of x squared plus 1. Okay, so right away, it's not a polynomial, it's a trig function. And trig functions, what do we know about them? They are periodic. So there's likely going to be lots of little minimas in this function. And in fact, well, we have the gradient there. And in fact, if we actually calculate out, if we actually plot out this function, we see a nice little complex graph with some minimas there, minimas that go extended down to -1, but also minimas that only extend down to 0, right? This 0 occurs because at 0, at x equals 0, this 1 comes into play. And so this 1 comes into play, then you have 0. Then you have sine of 0, which is 0, right? So this x squared plus 1, this plus 1, is screwing you over a little bit here. Although, what would the value of this function be if that plus 1 wasn't there? What would the function look like? This has nothing to do with machine learning, but you know, why not? Why not just have some fun? Yes, please, Patrick.
Well, x squared will become close to 0
Yeah.
equals 0, so log would become close to -infinity.
Yep.
So it would oscillate faster.
Yeah, basically it would go close to, it would reach negative infinity, yep. So it would just like oscillate faster, and then at 0 it's undefined. Yeah, good. Anyway, nice little aside. So that plus 1 helps us there. But the major point of this whole thing is that we have multiple minima here, okay? We have multiple minima here, and so since we have multiple minima, the question is where will the algorithm stop? So let's find the minimum. Let's use the same gradient descent algorithm. The only things I replaced were the actual gradients. Again, this is hand calculations. We don't need to do that. We don't necessarily need to do that, but we did that. And I calculated the actual, and I changed the actual function, f of x, to be sine of log of x squared plus 1. Okay? Yeah, so we have that. So if we plot out, if we do the gradient descent algorithm, we get, something. It's not completely, that doesn't completely make sense. What's happening here? Any ideas? Please tell me. The gradient is small in that case, yeah. But it shouldn't, like, how do we fix it? We could do a different initial guess, right? Should we do a different initial guess?
Wait, is it just like staying in place?
It's not staying in place, so that's a good idea. So let's see. So that's the first thing we should check. Is it staying in place? So it starts out at 1.7, and then it goes down to 1.68 to 1.6818. Okay, so it's not staying in place. It is decreasing. It is decreasing. So the gradient descent is working-ish. It's just incredibly slow. What do we change to fix it, to speed it up a little? Yeah, please, yeah. Yeah, exactly. I just did this so to get you guys thinking. So if we change it, I don't know, we chose 1e to the -3. Now let's do 10e to the -3. Still doesn't seem big enough. Let's do 100. Let's do 100. There we go. There we go. All right. So now we do appear to reach a minimum. So all's well. So you were right. The one issue here is that at this maxima, the gradient is very small, but so it doesn't move very much there. That sucks. But at the same time, it does move a little bit, and slowly we do get closer to minima. The gradient becomes larger, the step sizes become larger, and then as we get closer to the minima, the step sizes decrease again. So everything works out a bit. All we needed to do was increase the gradient a ton by 100-fold. So that's good. But what's the problem here? Yes, please.
It's getting stuck on local.
Yeah.
Not finding the absolute.
Yeah, exactly. We wanted to find the minima of the function. And the minima of the function, I mean, in this case, the minima of the function has multiple minimas. We have, it's periodic. It's not periodic because we have that log in there. But it has multiple minimas at -1. So we want to find a minima at -1. And probably we want to, depends on our application. We probably can't find all the minima. There's probably a function, there's probably a solution for the minima of all of this. Oh, there's definitely a solution. We could probably solve the function for the minima, for the function that defines the minima, the semi-periodic minima. But right here it goes, and it's just on the other side of this maxima, so it falls right into this well, which is at a minima of 0, right? So that sucks. Well, I could tell you that there's no algorithm alive that will give you the absolute minima of any function. Like, there's nothing that guarantees it, other than like brute force, I guess. If you brute force with like an infinite granularity, then I guess in theory that could happen. But you can't do infinite granularity, so there's no real algorithm that will give you the absolute minimum. So that sucks. So so this is a drawback of gradient descent. What can we do to hedge against this, though? Is there anything we could do if we really want the actual minima? A actual minima in this case? A better minima? Please, yeah.
Maybe you could like try different starting points.
Yeah. Yeah. You could try different starting points.
Just like compare where they landed.
So in this case, x in at 1.7. I don't know why I chose 1.87, but then let's do 1.9. Does that help us enough? Did that do anything? Oh, let's do, I don't know, 2.5. 0.9. There we go. Oh. And we're getting there. What should we do in this case? Should we increase the learning rate again? Maybe we'll just increase the number of iterations, huh? The number of iterations will just go to 1,000. There you go. And then we find a number of, and then we find the actual minimum. So in machine learning, this is called this has many names, but one common one is parameter space search. You initialize parameters to random values, and then you initialize them to multiple random values, and sort of find and optimize based off multiple random seeds. Okay, and then you get sort of minima. And what you'll find is that machine learning models, depending on the seed, you could get different results. You could get, if you're evaluating on well-known data sets, especially with the large language models, you could get 2 or 3% percentage point accuracy difference, depending on the seed that you choose. Which is why, if you're reading a research paper and they tell you my method led to a 2 to 3% improvement in accuracy, that's a red flag. It's possible to get that. It's possible to get that accuracy by choosing a different seed. Yes, I've seen it. Yes, I've proven that. Yes, I've proven that that happens. It sort of sucks, but that's just a pro tip for you guys. Okay, make sense? So, vary your initial point. You won't always. In fact, you'll hardly never be able to actually view the function like this. So you're going to basically do this gradient ascent. You're going to get an optimal value. And it's possible that that's the absolute best that's the optimized. Those are the absolute best optimized parameters you could get. That's very possible. But it's also very possible that it's just a local minima that your parameters got stuck in, and that there are other better local minima. So you should maybe try running it again at a different seed and just see if things improve. Okay? And also give more credence to people that actually do this. There are some it should be more common practice, but the way to handle this is basically to train multiple different models and have a range, and to define a range of accuracies instead of just a single accuracy number, which I'm a big proponent of, but isn't enforced, unfortunately, in major conferences. Anyway, sorry, I don't want to be salty, but man, you guys have no idea how much time I wasted trying to replicate results of papers where it's just awful. All right, anyway, so enough salt. So we did that gradient descent. We beat that into the ground. So let's take it a step further, and let's talk about automatic differentiation. So the thing with the other examples that we did, we had to do, okay, so the main idea with that gradient descent is that we have a learning rate, and we take a step size that is proportional to the gradient, right? And so the previous examples, we calculated out the gradient manually, and then we multiplied by that by the learning rate and took this step size like that, right? Now, PyTorch PyTorch and Python in general doesn't do things symbolically, right? The computers don't like to do things symbolically. They are bad at it. So what are the options that we could choose? How do we calculate the differential? How do we calculate the gradients? How do we differentiate? How do we derive it? How do we calculate the derivative without actually symbolically calculating the derivative, right? So, I mean, the symbolic we did. So we could also do this numerically, right? That was something we talked about extensively, that we just perturb the points a little bit, right? We have a particular point, and we just look slightly to the left at that particular point, evaluate the function at the left, and then take the slope there. That gives us an approximate value for the slope at a particular point, right? This is a very common thing that computers have been doing for like 100 years, since the dawn of computers. That's been basically the most popular way to guess a slope, is basically perturb the point a little bit. You have a point, you take that point plus 0.0001 to the left, that point plus point, and then you perturb that point a little bit, you evaluate it on the perturbation, you evaluate it on the actual points, you take the slope, bam, you have the gradients at that point, right? Very reasonable thing to do, computationally expensive, okay? Especially with a lot of different parameters and such. So a better option is what we did last lecture. We construct a computation graph, right? We compute the value of the function at a particular point using a forward pass, and then we compute the derivative at a particular point using the backward pass. And then we do this via accumulation of the chain. We do this via accumulation using the chain rule. And so doing things this way allows us to reuse values. We compute the function twice. It's not the worst thing in the world, but it does mean we have to compute the function at least twice, and we have to perform a division, which is costly. Divisions are always costly, and it's not exact, right? This backpropagation, we could reuse a lot of the computed values when we do the forward and back propagations. And what's more important is that we're not doing an estimate of the we're not getting an estimate of the gradient. We are getting the actual value of the gradient itself. It's a much more stable process. Okay, as much parameters we could remove from our optimizations, the better. We don't want to keep having fitting parameters everywhere. We are engineers. I, more than anyone, am totally sympathetic to putting fitting parameters and making things work as the next guy. But ideally, we shouldn't want to do that, okay? So that's the beauty of backpropagation, where we construct a computational graph, we calculate the function value in the forward pass, and then we calculate the function derivative at that point in the backward pass, and then we use those values to do gradient descent, okay? So before we get to that, actually, the slides are a little out of order. Before we get to that, one thing one notion I want to introduce is the objective function. The objective function is the idea that maybe we don't want to calculate the minima. Maybe we want to calculate the value of x where f is equal to 0.5. Okay? So how do we do that? And how can we do that? It's fairly simple. We simply create a new function that wraps around the previous function. Okay? We create a new function that wraps around the previous function. We say we have the previous function, and we say we want to minimize this new function that is smallest when f of x is equal to the value we want to obtain. Okay? And we square it mainly because we want positive and negative errors to be treated the same, and we don't want any negative values from this objective function. But the idea here is that instead of basically always having to calculate what value f of x is equal to 0, now we minimize this whole function. And so if we minimize this whole function and we set y equal to 0.05, then we will calculate the value of x for which f of x is equal to 0.05. Because when f of x is equal to 0.05, y is equal to 0.05, and this whole thing becomes 0. Okay? So this is what's known as the mean squared error loss function. It's basically the hello world of loss functions. We'll discuss different loss functions later, but this does the job in 90% of the cases fairly well. So same thing. Let's try the example that we had before. We had f of x. We have this loss function f of x. And so we want the derivative of this loss function. We want to take the gradient of this loss function, which is we set y equals to 0.05. So we take the derivative of 0.05 minus f of x squared. So it's 2 times 0.05 minus f of x times the gradient of f of x dx. Okay? So the code would look something like this, where all we've done is change the gradient to include the gradient of the objective function. And so if we actually calculate the graph, if we actually do the graph again, we see that if we take gradient descent, we start at 1.7 and we go down and we reach a value where y is equal to 0.05. Okay? So that's the objective function. That's how an objective function works. We don't necessarily have to always optimize for a particular function equal to 0. We optimize for a particular function that we want equal to something. Okay? So as you can imagine, this becomes relevant when we're discussing data, when we're trying to fit a model to a particular piece of data. This is where that becomes important. Does that make sense? All we need to do is wrap the original function up in an objective function, i.e. we wrap it up in a new function where this new function is minimized when f of x matches some predefined value that we care about. Okay? And doing things like this allows us to optimize, allows us to use gradient descent to find the value of x for which y equals a particular value, in this case 0.5. Okay? All right. So, brief diversion. Oops. Come on. There we go. So, if we want to match multiple data values, we can simply change the loss function. We call it you could call it the loss function also. We could change it so that the loss function, or the objective function, is dependent on each one of the data values. So if we have multiple values for which we want y to be equal to, we simply calculate the loss for each one of those values. Okay? And so for in this case, in the case of this single the single function, single parameter, it doesn't make sense. But if you have multiple parameters, you want to optimize, you want to average out those multiple parameters so that they match all your data as good as possible. And there will be conflicts, but that's the idea behind machine learning, is that you won't be able to get you won't be able to match every single data point correct exactly, but you will be able to minimize the loss in this case. Okay? But the loss doesn't necessarily have to go to 0. It could stay at some high value. It just has to go to some particular minimum, which is what gradient descent does. It always tries to minimize the function. Okay. All right. So sorry about that. That was that slide. This slide was a bit misplaced. But back to the automatic differentiation. The backpropagation is simply we construct a simple computational graph of a function, and then we calculate out the derivative and gradient rules to get the gradients and accumulate the results versus the chain rule. And there we go. There we go. Now I'm back on track. So we have a particular computation graph here. Could anyone quickly tell me what function this is representing? We have x, so there's one parameter input, and then there's one input here, there's one x, and then there are a couple different parameters. So in this case, we have a, b, and c parameters. So let's say x is propagated, w1 is simply equal to x, it's just a fan out. So this becomes x, so w2 outputs x squared, and then w3 outputs a times x squared, okay? And then that goes to w5, which has multiple inputs coming into it. w1 x, and it goes bx, okay? So bx, it gets added to ax squared, okay? And then we add c to that also. So we get ax squared plus bx plus c. That is the function we have. Makes sense? And then well, we have this little bit at the end here. We have the objective function. We have the particular data we are trying to match, another inputs. And then we pass it to W7, where W7 outputs y minus this function squared. Okay? So it outputs, so the total computation graph goes to this objective function. To the computer, when we tell PyTorch we want to minimize a particular function, we give it this function, right? The computer doesn't know if we're giving it the actual function that we're trying to fit to a piece of data or the loss function. It just knows that we get a function. I want to find a set of values that make the function as small as possible. Okay? And we use that. We use that by simply saying, okay, we wrap our function up into a new function, and then we minimize this so that we could match this function to this particular output. Everyone with me there? Okay. So we calculate the gradients like we did before. And namely, what we're trying to do in this case, we have a particular input, and we're trying to match, and we're trying to fit this function to a particular output value. Okay? So really, what we want to do in this example is change the values of a, b, and c so that when x is equal to some value, it will, when we put it through the function, ax squared plus bx plus c, when we put it through that function, we get out yi. Okay? So instead of trying to find the x that gives you a particular value, we have what x is, and we're trying to find the parameters of the function that give you a particular value. Okay? So what we do here is simply optimize from the loss function down to. We optimize from the loss function. We backpropagate. We get the gradients for each of the functions here. So the gradients for the loss function we backpropagate. It's equal to 1. We backpropagate W7, which is equal to 2 times the y minus the loss function. That's there, and so on. And so eventually we come up with the gradients for A is -2 times W2 is x times y minus the function ax squared plus bx plus c. The gradient for c is equal to 2 times that loss function, not squared. And b, the gradient for b is -2 times x times the y minus the function. Okay? We just perform the same back propagation we did before. And what happens? Well, now we could, come on. So we do the same back propagation we did before. We have a set of parameters. We use the theta symbol to represent these set of parameters involved in a particular function. And we simply say that we want to optimize the set of parameters so that for this, we want to optimize the set of parameters and change them at every step of the gradient descent so that the loss between the two functions, there we go, so that f of x is equal to y. I don't know why I didn't put that there. But we want to change the parameters in a way so that it becomes closer to a certain set of data points. We have a set of data points here. We have the set of values that the functions at a particular parameter of a particular theta k give there. And then we change the parameters ever so slightly every step in order to get closer to the y data points. So for instance, if we look at the actual code here, let's say we have a ground truth. Okay, we have a ground truth where A is equal to 3, B is equal to 2, and C is equal to 1. Okay, this will be our data set. This is our ground truth data set where, this is where we'll just calculate 20 points so that we have something that we could optimize to. Okay, and then let's try and see if we could recreate this function without using these values. Let's see if we could recreate this function, starting with initializing A, B, and C to some random values, and then initializing them to some random values. This is just to record the values as the gradient descent occurs, and then we'll calculate the error, and then we calculate the gradient for each of the functions, depending on the value of y. Okay, so remember here, y is a vector of data, and we will calculate the error for each piece of data against whatever the current set of parameters gives us. Okay, and then we change the set of parameters based on the gradients that we calculated for them. Change the set of parameters based on gradients we calculate for them. And so, after we do this 100 times, I'm guessing? 100, oh no, editor. What did I say, editor to? Oh yeah, 100 times. After we do this 100 times, we sort of see what the final guess we get is. And if we look at the graph, doesn't allow me to, one sec, let me just, could. Everything's so tiny. Yay, okay. Nope, nope, okay. If we do this 1,000 times, we start off with a function that doesn't match the data at all. But after a few iterations, we get a curve there that matches the function more. And then we get a bit more of a curve, and a bit more of a curve, and a bit more of a curve, until we get something that's pretty close. Okay? And if we actually look at the mean squared error for this function, we see that after 20, we see that the error between the function that we start off with at the very start, when the a, b, and c are just random numbers, we see that the error is very large. But then as we run gradient descent, especially around iteration 20, where you get a nice curve going, the error greatly decreases. And then if we keep running gradient descent, we get closer and closer to the ground truth values. Does that make sense? So all we're doing, very simple. We wrapped up the original function, has some parameters. We generated some sample data. We wrapped up the original function in the mean squared error, and then we backpropagated on A, B, and C. Okay, and so, there we go. So this is even easier in PyTorch. This is even easier in PyTorch because you don't need to calculate the gradients itself. You could simply do the same thing. You could do the same thing. Basically, you calculate the error, and you simply calculate the mean squared error here, the loss function. You're not even calculating a gradient for A, B, and C. You're not calculating a gradient for A, B, and C. You're literally only calculating the loss, and then you're calculating the backward gradient by simply saying loss backward. You're calculating that gradient, and for each of A, B, and C, you are simply finding the gradients of A, of B, of C, and then multiplying it by some learning rate and changing it like so. Okay, so we didn't even really need to do the backpropagation ourselves. PyTorch is doing that for us, right? PyTorch is doing that for us, and we are just benefiting because PyTorch says backward lost that. Because when we say lost that backward, PyTorch is literally running that gradient, that backward gradient accumulation for us. And then all we need to do to find the actual values of the derivative of the loss with respect to A is simply say A dot gradient, and then we multiply that alpha, and then we get the step for A, and then we visualize it the same we did. It's like so. We have the actual function, ground truth data, and then the function slowly matches more and more. Okay? I don't know why it's getting cut off, but this is all visible in the notebook if you want to take a look. Okay, just some points that we wanted to, to emphasize. You need to turn requires gradient on. So when we initialize x and a and b and c, you need to make sure the requires gradient is, not x. When we initialize b, a, b, and c, we want to make sure it requires gradient is set to true so that the program knows, yes, these functions will need to calculate the gradient for these functions. That's why you should start creating the computation graph, literally when we initialize them, and whenever we perform an operation with those variables, continue to update the computation graph. That's all it requires grad is doing. It's just telling the computer, this will become important. These parameters will become important. Please keep track of them. All you're doing there. And then there's a couple of little things. .data.item gives you access to the actual value in the tensor, not the tensor itself. Some of these are necessary from a technical sense, but the reason why is to avoid certain outlier cases. It's good practice. But you could get away with not using, for instance, you could get away with not using detach.numpy and torch.nograd if you're not writing to the actual parameter value. But these are just things to be aware of. It's good practice. But you guys could experiment with your own, see what happens. All right, so last function. Remember the sigma function that has two parameters, b and tau, that change the inflection points and the shape of the sigmoid function. That change the inflection point and the shape of the sigmoid function. So we could do the same thing there. We don't have to just work with parabolas. We could literally generate some data points we want to fit, generate an initial guess of the parameters, go through the backpropagation process like so. Remember, we're doing the same thing that we did before, except f of x is now equal to sigma function. And all we're doing is literally, we're just computing loss step backwards. The loss is literally y minus f of x squared. We're computing loss, we're saying loss step backwards. Torch, please compute the backward gradient for us. And then we're altering b and tau we're changing them by the learning rates and by their gradients, respective gradients. And then doing all of this gives us a nice little fit. So we start off with something that doesn't match the curve at all. I mean, it starts off at 0 and doesn't match the curve very much. But after a couple iterations, we get something that matches the curve pretty much perfectly. Okay? So play around with the learning rate, play around with the different parameters, with the different functions. After doing this a couple times, you'll get the hang of it very quickly. But yeah, that's it for today. There we go. And so have a good weekend. Homework 2 is due Monday, and I guess I'll see you guys next week. Thank you. Thank you.